In October 1999, a supercyclone struck the eastern coast of India. Winds exceeding 250 kilometers per hour drove a massive storm surge inland, flattening coastal infrastructure and wiping out entire settlements. By the time the water receded, an estimated 10,000 people were dead. 20 years later, Cyclone Fani made landfall in the exact same region. Meteorologically, Fani was an equally severe storm, packing sustained winds approaching 200 kilometers per hour. Yet the casualty count dropped nearly to zero. Before the first rain fell, authorities had successfully evacuated 1.2 million people to safety. No major upgrades to the fleet of rescue helicopters or physical response hardware account for this change. Spatial data and mitigation mapping provided the invisible architecture that kept 1.2 million people out of the storm's path. This is the disaster management cycle, the operational framework used by government agencies to organize hazard planning. The left side contains mitigation and preparedness. These are the analytical tasks executed years and months before a hazard exists, mapping topography, enforcing building codes, and planning evacuation routes. The right side covers response and recovery. These are the urgent, high-visibility actions taken in the minutes to weeks immediately following an event. Many agencies commit a pervasive administrative error, over-investing in the right side while chronically underfunding the left. They prioritize visible response hardware, like drone fleets, over the invisible GIS capability required for mitigation. A $50,000 rescue drone cannot help a community that was permitted to build in an unmapped high-risk floodplain. This satellite capture shows a massive weather system. While a meteorologist sees wind speed and barometric pressure, a district commander needs local specificity to organize an evacuation. Raw meteorological data lacks that detail. To truly save lives, that data must undergo impact-based forecasting, a process that translates atmospheric physics into localized human consequences. This requires a layered GIS stack. A 3D topographic digital elevation model forms the foundation. Overlaying the cyclone track generates a storm surge inundation footprint. Injecting census and infrastructure data into this flooded zone outputs precise, block-level, mandatory evacuation polygons and optimized escape routes. The physical reality of Cyclone Fani was devastating. Transit networks were shredding, and infrastructure was destroyed under the force of the wind. Yet the death toll remained near zero because these systems translate meteorological math into survival zones. Identifying precise coordinates for resource deployment is the primary challenge of the active response phase. During events like the Uttarakhand forest fires, monitoring operates on a two-tier architecture. The macro tier relies heavily on the ISRO satellite network to conduct wide-area thermal screening across thousands of square kilometers. However, satellites are restricted by orbital revisit windows. Their thermal sensors are also frequently blinded by dense cloud cover or the fire's own smoke plume. This requires the micro tier, tactical multi-rotor drones designed specifically for subcloud operation. The protocol functions as a strict handoff. The satellite detects a broad thermal anomaly from orbit, and the drone is deployed to those exact coordinates to map the live fire perimeter from just above the tree line. Look at the terrain. Ground verification across these steep ridges is too slow and hazardous for firefighting crews to attempt without this aerial handoff. Effective hazard response relies heavily on this coupled architecture. Satellites flag the macro quadrant, and drones verify the micro coordinates. This image of the 2024 Wayanad landslides illustrates the limits of aerial response. Drones generated rapid topological maps of the shifting debris, guiding ground teams safely. However, optical and thermal sensors cannot penetrate meters of dense mud and rock to locate buried survivors. Believing hardware is magic leads to operational failure. Drones augment the response, but they can never replace geophysical ground search and K9 units. As the timeline extends into the recovery phase, the requirement shifts from live life-saving video feeds to systematic mathematical surveys. This relies on a photogrammetry pipeline. Drones capture thousands of overlapping top-down images, which specialized software stitches together into a geometrically precise 3D model. Authorities use this 3D map to calculate exact volumetric estimates of debris, providing the data required to issue accurate government clearance contracts. By comparing pre-disaster baselines against the new 3D model, the system automatically classifies structure-by-structure damage to allow for rapid financial compensation. Effective recovery produces the high-fidelity economic data needed to authorize and finance the entire reconstruction. The disaster management cycle is a closed loop. The precise 3D data captured during recovery must immediately overwrite the outdated base map used in the mitigation phase, ensuring the next risk assessment reflects the current geographic reality. The drone is merely a peripheral data capture device. The Geographic Information System that processes and interprets that data is the true central engine. True disaster resilience relies on using spatial data to ensure the population is nowhere near the storm when it hits.